Today we are going to learn test for absolute convergence. Test for absolute convergence. For absolute convergence. Let sigma n is equal to 1 to infinity and sigma bn n is equal to 1 to infinity be two series of real numbers. We say that sigma an is dominated by sigma bn if there exists positive integer capital N such that mod of an is less than or equal to mod of bn for all small n greater than or equal to capital N. That is, mod an is less than or equal to mod of bn except for finite number of values of n. In this case, we write sigma an is dominated by sigma bn, sigma an less than sigma bn. Sigma an is dominated by sigma bn. Definition. Let sigma n is equal to 1 to infinity and sigma bn n is equal to 1 to infinity be two series of real number. Be two series of real numbers. Two series of a real number. We say that summation n is equal to 1 to infinity is dominated by summation bn n is equal to 1 to infinity if there exists positive integer capital N. If there exists positive integer capital N, or you may write capital N belongs to I, such that mod of an less equals mod of bn for all small n greater than or equal to capital N. For all small n greater than or equal to capital N. That is, mod of a suffix capital N less than or equal to mod of b suffix capital N. Mod of a n plus 1 capital N plus 1 is less than or equal to mod of a n plus capital N plus 1, and so on and so on. That is mod an is less than or equal to mod of bn except for finite number of values of n. Except for finite number of values of n. Finite number of values of n, small n. In this case, we write sigma n is equal to 1 to infinity is dominated by sigma bn n is equal to 1 to infinity. N is equal to 1 to infinity. For example, For example, let sigma an is equal to sigma n is equal to 1 to infinity, is equal to minus 1 raised to n, minus 1 raised to n is equal to 1 to infinity upon n square. Summation n is equal to 1 to infinity minus 1 raised to n upon n square, and sigma bn n is equal to 1 to infinity is equal to sigma 1 upon 2n plus 1, n is equal to 1 to infinity, n is equal to 1 to infinity. Here mod of an, sigma mod of an, summation mod of an is equal to 1 to infinity is equal to summation n is equal to 1 to infinity 1 by n square, which is equal to 1 upon 1 square, that is 1, plus 1 upon 2 square, that is 4, plus 1 upon 3 square, that is 9, plus 1 upon 4 square, that is 16, plus and so on. Sigma mod an. Sigma mod bn, sigma mod bn, n is equal to 1 to infinity is equal to sigma n is equal to 1 to infinity 1 upon 2n plus 1, 2n plus 1. If we put n is equal to 1, we obtain 1 upon 3 plus, if we put n is equal to 2, 2 into 2, that is 4 plus 1, 1 by 5, 3 into 2, that is 6 plus 1, which is equal to 1 by 7. If we put n is equal to 4, we obtain 1 by 9, plus and so on, plus and so on. Here 1 is greater than 1 by 3, that is a1 is greater than b1, a2 is also equal to 1 by 4, which is greater than 1 by 5, that is a2, mod a2 is greater than mod b2, and from a3, a4 and so on, mod an is less than or equal to mod of bn for all n is greater than or equal to 3. Clearly, mod a1 is greater than or equal to mod b1, that is 1 is greater than 1 by 3. Mod a2 is also greater than or equal to mod b2, that is 1 by 4 is greater than 1 by 5. But mod an is less than or equal to mod of bn for all n greater than or equal to 3. Here capital N, that is positive integer capital N, is equal to 3. Capital N is equal to 3. Therefore, sigma an is dominated by sigma bn, that is summation n is equal to 1 to infinity minus 1 raised to n upon n square is dominated by sigma 1 upon 2n plus 1, n is equal to 1 to infinity. Here capital N is equal to 3, positive integer is 3. Therefore, sigma minus 1 raised to n upon n square is dominated by sigma 1 upon 2n plus 1. N is equal to 1 to infinity. n is equal to 1 to infinity. This result, mod an is less than or equal to mod bn, is not true only for n is equal to 1 and n is equal to 2. That is, for finite number of values of n, except for finite number of values of n. Therefore, this series sigma an is dominated by series sigma bn. Sigma bn. Now we see comparison test. Comparison test. That is theorem number 1. Theorem number 1. Theorem number 1. Comparison test. Comparison test. If sigma an is dominated by sigma bn, if sigma n is equal to 1 to infinity, is dominated by sigma bn, n is equal to 1 to infinity, where sigma bn converges absolutely. Sigma bn n is equal to 1 to infinity converges absolutely. Then sigma an also converges absolutely. Sigma an is equal to 1 to infinity also converges absolutely. Sigma an is equal to 1 to infinity also converges absolutely. If sigma an converges absolutely, then we write sigma mod an less than infinity. If sigma an converges absolutely, then we write sigma mod an less than infinity. Symbolically, we write this comparison test. We write this comparison test as if sigma an is dominated by sigma bn, sigma n is equal to 1 to infinity is dominated by sigma bn, n is equal to 1 to infinity, and sigma mod bn is less than infinity, and sigma mod bn is less than infinity, n is equal to 1 to infinity, then sigma mod an is also less than infinity. Then sigma mod an is less than infinity, n is equal to 1 to infinity. This is the statement of comparison test. Since my hypothesis sigma bn converges absolutely, sigma bn converges absolutely. Therefore, sigma bn converges. Proof. Since my hypothesis sigma mod bn is less than infinity, n is equal to 1 to infinity. That is sigma bn converges absolutely. That is sigma bn n is equal to 1 to infinity converges Absolutely. Sigma Bn converges absolutely. Absolutely convergence implies convergence. That is theorem number 1 on absolute convergence and conditional convergence. Sigma Bn converges. Therefore, sigma Bn, n is equal to 1 to infinity, converges to say capital M. Sigma Bn converges to capital N. If the series sigma An converges to capital A, then we write sigma An is equal to A. That is sigma Bn is equal to A. Sigma mod Bn converges by definition of absolutely convergent series. By definition of absolutely convergent series, sigma mod Bn converges. It converges to say capital M. That is sigma mod Bn is equal to capital M. N is equal to 1 to infinity. M is equal to 1 to infinity. Let Sn is equal to, S suffix n is equal to, S suffix n is equal to mod A1 plus mod A2 plus mod A3 plus and so on plus mod of An for every n belongs to I. That is, Sn is nth partial sum of the series sigma mod An, summation mod of An. Sn is nth partial sum of series sigma mod An. If small n is greater than or equal to capital N, if small n is greater than or equal to capital N, then Sn is equal to mod A1 plus mod A2 plus and so on mod A3 modulus of A3 plus and so on plus mod of A suffix capital N minus 1 plus mod of A suffix capital N plus mod of A suffix capital N plus 1 plus and so on plus mod of A suffix small n for every n belongs to I. For every positive integer n belongs to I. This is, say, statement number 1. Sigma mod Bn converges to M. This is, say, statement number 2. Since my hypothesis sigma An is dominated by sigma Bn, since by hypothesis sigma An, n is equal to 1 to infinity, is dominated by sigma Bn, n is equal to 1 to infinity. Therefore, by definition of dominated series, by definition of dominated series, by definition of dominated series, there exists positive integer, capital N, or n belongs to I, such that I is set of positive integer, such that mod of An is less than or equal to mod of Bn for every small n greater than or equal to capital N. This statement says that mod A suffix capital N less than or equal to mod of B suffix capital N. Mod A suffix capital N plus 1 is less than or equal to mod of B suffix capital N plus 1. Mod of A suffix capital N plus 2 is less than or equal to mod of B suffix capital N plus 2, and so on, and so on. This is a 3. Using 3 in RHS of 2. Using 3 in RHS of 2. We obtain Sn is less than or equal to mod A1 plus mod A2 plus and so on plus mod of A suffix capital N minus 1. Mod A suffix capital N is replaced by mod of B suffix capital N. Mod of B suffix capital N plus 1 plus and so on plus mod of B suffix small n. For every positive integer, n belongs to I. N belongs to I. Therefore, we write this S suffix small n is less than or equal to mod A1 plus mod A2 plus and so on mod of An minus 1 plus capital M, since sigma mod Bn converges to capital M. Therefore, this partial sum converges to capital M. Therefore, we write S suffix small n is less than or equal to mod A1 plus mod A2 plus and so on mod of An minus 1 plus capital A for every n belongs to I. This statement is true for every n belongs to I. Therefore, sequence Sn n is equal to 1 to infinity is bounded above. Therefore, sequence S suffix n is equal to 1 to infinity is bounded above. Sequence of partial sum Sn n is equal to 1 to infinity is bounded above. Sn is by 2. Sn is sequence of non-negative terms. Sequence of non-negative terms. From 2 sequence Sn n is equal to 1 to infinity is sequence of non-negative terms or numbers. Therefore, by theorem 1 on, by theorem 1 on series with non-negative terms, series of non-negative terms or numbers. Sequence of partial sum converges, therefore bounded above, therefore sigma mod An converges. Therefore, sigma mod n is equal to 1 to infinity converges. Therefore, by definition of absolutely convergent series, sigma an converges absolutely. Therefore, by definition of absolute convergence of series, sigma n is equal to 1 to infinity, converges absolutely. That is sigma mod an less than infinity. Hence the proof of comparison test. Now we see second theorem. Theorem number 2. If sigma an is dominated by sigma bn, if sigma an is equal to 1 to infinity, is dominated by sigma bn, and sigma mod an is equal to infinity, summation mod an is equal to infinity, then sigma mod bn is equal to infinity. Sigma mod bn n is equal to 1 to infinity is equal to infinity. That is if sigma an is dominated by sigma bn, if sigma an n is equal to 1 to infinity is dominated by sigma bn, and if sigma mod an is equal to infinity, mod an is equal to infinity, then sigma mod bn is also equal to infinity. Since by hypothesis sigma an is dominated by sigma bn, proof. Since by hypothesis sigma an is equal to 1 to infinity is dominated by sigma bn, that is sigma an is dominated by sigma bn and is equal to 1 to infinity. Symbolically, we write sigma an is dominated by sigma bn. By definition of dominated series, by definition of dominated series, there exists positive integer capital N. There exists positive integer capital N n belongs to I, such that mod an is less than or equal to mod of bn. Mod an is less than or equal to mod of bn for all small n greater than or equal to capital N. For all small n greater than or equal to capital N. Since my hypothesis sigma mod an is equal to infinity, since my hypothesis sigma mod an is equal to infinity, n is equal to 1 to infinity. That is, sigma mod an diverges to infinity. Diverges to infinity. Let Tn is equal to, or you may take Sn also. Let Sn is equal to mod a1 plus mod a2 plus and so on mod an for all n belongs to I. Mod an belongs to I. Let Sn is equal to mod a1 plus mod a2 plus and so on plus mod of an for every n belongs to I. Since sigma mod an diverges, therefore sequence of partial sum Sn also diverges to infinity. Since sigma mod n is equal to 1 to infinity, diverges to infinity. Therefore, by definition of divergence sequence, divergence divergence series, sequence of partial sum Sn, n is equal to 1 to infinity, diverges to infinity. That is, limit n tends to infinity of Sn is equal to infinity. This is statement number 2. Let Tn is equal to, T suffix n is equal to mod of b1 plus mod of b2 plus mod of b3 plus and so on mod of bn for every n belongs to I. For every positive integer n belongs to I. If small n is greater than or equal to capital N, then we write Tn is greater than or equal to, or we first write Tn equals mod b1, mod b2, mod b3 plus and so on mod of bn minus 1 plus mod of bn plus mod of bn plus 1 plus and so on plus mod of b suffix small n. And this is greater than or equal to Tn greater than or equal to by using 1 in RHS of 3. This is a 3. Using 1 in RHS of 3. RHS of 3. We write Tn is equal to Tn greater than or equal to mod a1 plus, not mod a, mod b1. Here is mod b1 plus mod b2, mod b1 plus mod b2 plus mod b3 and so on mod of bn minus 1 and this mod of B suffix capital N is greater than or equal to mod of An plus mod A suffix capital N plus mod of A suffix capital N plus 1 plus and so on mod of A suffix small n, last term is small n, for every n belongs to I. Every n belongs to I. Therefore, Tn, T suffix n, is greater than or equal to mod B1 plus mod B2 plus and so on plus mod of B suffix n minus 1 plus S suffix n minus some finite term, that is mod A1 plus mod A2 plus and so on plus mod of A suffix n minus 1. Taking limit on both the sides as n tends to infinity. This is true for every n belongs to I. Every n belongs to I. Taking limit on both the sides as n tends to infinity, we obtain limit n tends to infinity of Tn greater equals limit n tends to infinity of RHS. RHS, that is mod B1 plus mod B2 plus mod B3 mod of Bn minus 1 plus Sn minus mod A1 plus mod A2 plus and so on plus mod of An minus 1. An minus 1. As n tends to infinity, Sn diverges to infinity by 2. That is, this is limit of RHS is equal to infinity. Infinity. Limit of RHS is equal to infinity. Therefore, limit n tends to infinity of Tn is equal to infinity. Sequence Tn n is equal to 1 to infinity diverges to infinity. Diverges to infinity. Therefore, by definition, corresponding series sigma mod Bn diverges to infinity. Therefore, by definition of divergence series, divergence series, sigma mod Bn diverges to infinity. Sigma mod Bn, n is equal to 1 to infinity, diverges to infinity. That is, sigma mod Bn is equal to infinity. Is equal to infinity. N is equal to 1 to infinity. Hence the proof of theorem number 2. Theorem number 2. Now we take the theorem number 3. Theorem number 3. Statement of theorem number 3. 3a and 3b. If sigma Bn converges absolutely, if sigma Bn n is equal to 1 to infinity converges absolutely, and if limit n tends to infinity of mod of An upon mod of Bn exist, then sigma An converges absolutely. Then sigma An n is equal to 1 to infinity converges absolutely. Converges absolutely. B, if sigma mod an is equal to infinity. B, if sigma mod an is equal to infinity, and if limit n tends to infinity of mod an by bn exist, then sigma bn mod bn is also equal to exist, then sigma mod bn n is equal to 1 to infinity is equal to infinity, This is a theorem number 3, 3b and 3a, 3b and 3a. Proof of this theorem. In theorem number 3a, limit n tends to infinity of mod an upon mod bn exist, and theorem B, limit n tends to infinity of mod an upon mod bn exist. In both the part A and B, there is common hypothesis, limit n tends to infinity of mod an by mod bn exists. Since by hypothesis limit n tends to infinity of mod of an by mod of bn exists. If the sequence Sn n is equal to 1 to infinity has a limit L, then we say that sequence Sn n is equal to 1 to infinity converges to L. This limit exists. Therefore, sequence mod an upon mod bn n is equal to 1 to infinity converges to some real number, say capital M. But we know every convergent sequence is bounded. That is theorem in bounded sequences. But we know every convergent sequence of real number is bounded. But we know theorem, every convergent sequence of real number, convergent sequence of a real number is bounded. Therefore, for some m for any real number m, or for some m greater than 0, therefore for some m positive real number m greater than 0, mod of an upon mod of bn is less than or equal to capital M for every n belongs to I. That is, mod of an is less than or equal to capital M times mod of Bn for every positive integer n belongs to I. For every positive integer n belongs to I. Sigma mod An is less than or equal to sigma mod An is less than or equal to sigma m times mod Bn. N is equal to 1 to infinity. N is equal to 1 to infinity. Sigma mod An is less than or equal to sigma m times mod Bn. This statement says that sigma An is dominated by m times sigma mod Bn. Sigma m is real number, therefore we write this as sigma summation mod An is less than or equal to capital M times summation n is equal to 1 to infinity mod of Bn. Mod of Bn. This is statement number 1. Now we prove A. First part A. Since by hypothesis sigma Bn converges absolutely. Since by hypothesis sigma mod Bn is less than infinity. That is, sigma Bn converges absolutely. Converges absolutely. This is a statement number 2. From 1, 2 and comparison test or theorem number 1, we say that sigma mod An converges. From 1, 2 and theorem 1. Theorem 1. Or you may write comparison test. Sigma mod An converges. Sigma mod An converges. That is, or comparison test. Comparison test. Sigma An, n is equal to 1 to infinity, converges absolutely. Converges absolutely. Now we prove B. B. Since by hypothesis of B sigma mod An is equal to infinity. Since by hypothesis sigma mod An is equal to infinity. Equal to infinity. This is a statement number 3. From 1, 3 and theorem 2. Therefore, from 3, 1 and theorem 2. Theorem 2 above. Sigma m times sigma mod Bn converges or diverges. Sigma m times summation n is equal to 1 to infinity Bn mod Bn diverges to infinity. Diverges to infinity. Since m is positive real number, therefore sigma mod Bn diverges. Sigma mod Bn, n is equal to 1 to infinity, diverges to infinity. In this case, we write sigma mod Bn is equal to infinity. Sigma mod Bn is equal to infinity. Hence the proof of part B. Hence the proof of theorem part A and B. Thank you for watching the video.